Okay, dear colleagues, I'm from the Technical University of Sofia. Okay. The aim of our research is to look for opportunities for non-destructive thermal detection of defects in Prepreg layer of multi-layer printed circuit boards, called PCB for short. Defects detection, such as air cavities or airs in poor adhesion in lamination of Prepreg sheets in the production of multi-layer PCBs, leads to improved quality and reduced production costs. I will briefly explain what infrared thermal flow detection is, because I saw from the schedule of the conference that the composition of the presenters is diverse. Similar to X-ray diagnostics, for example, the internal structure of the test object can be visualized and inhomogeneity is detected, but infrared thermography is completely safe for both the operator and the test subject. An infrared camera measures the surface temperature of the object under study during or after its thermal excitation. Such thermal excitation can be optical using a halogen lamp or flash lamp, ultrasonic, electromagnetic, magnetic, or otherwise induced. Depending on the type of heat excitation source, its mode of operation, pulsed or harmonic or other, the method of processing the sequential thermal images taken by the infrared camera, more than 46 different procedures of the method are known. There is no universal procedure that detects different types of hidden defects in different materials. Finding the right procedure is a long, expensive process and may not ultimately lead to the desired result in practice. On the other hand, it may turn out that with these numerous thermographic procedures, it is not possible to realize non-destructive diagnostics for certain types of defects in certain layers of materials. In such cases, another suitable non-destructive method is sought, such as ultrasonic, electromagnetic, or otherwise. Nowadays, infrared cameras, which are the main tool in thermal non-destructive diagnostics, are becoming more and more accessible, and testing is non-contact and can be performed for moving objects and large areas. This allows the development of a thermographic system for continuous monitoring simultaneously and on a large number of PCBs.
Sorry to
For this
interrupt.
purpose,
Doctor, your slides are not moving. Yeah,
yes.
now it's fine. Okay.
For this purpose, about 20 parameters must be known for the measurement setup for the effective automation of the process of non-destructive thermal diagnostics. Prepreg is impregnated with resin in a water composite material. The non-destructive detection of hidden defects in composites using infrared thermography has been extensively studied. However, in the case of multi-layer PCB, the Prepreg material is hidden, and hidden defects must be found in it. This complicates the task, firstly, because due to the specific of the PCBs, the same size and depth of available defects may be located under different layers with different thermophysical parameters. That is, the environment in which these defects of Prepreg are located has a known anisotropy. All performed thermographic examination of composite materials to detect defects in them look for appearance of temperature differences on the surface of composite materials as a sequence of its impaired anisotropy due to the existing defects. In our case, the task is more complicated because the Prepreg layer is hidden under the surface of the PCB under a different number of tapes and layers. What are the features of Prepreg for multi-layer PCBs? The PCB thickness depends on the type of Prepreg used. The required thickness of the Prepreg layer can be achieved by using more than one Prepreg sheet. Resin content in the Prepreg decides how thick a sheet of laminate will be when it is pressed. The content also has a considerable effect of properties such as dielectric constant, coefficient of thermal expansion, and drilling and etching quality. What research approach did we use and what results we get? First of all, we have Prepreg test samples with artificially manufactured defect of cavities in dielectric Prepreg layer. One important feature of the samples is that the topology of the copper foil of course has been formed. This topology is such that it models various defects in the conductive copper layer on both sides in the Prepreg. In aim is to see their influence on the recognition of defects in the Prepreg layer. Second, different, here you can see the digital three-dimensional models of the test specimen were made by using specialized software. Here you can see the parameters of these models. Such good detection is obtained by using here the results of the different models with different defects in Prepreg, also results after simulation. Here also results when we can see the defects in simulated defects in Prepreg after lock-in thermography simulation. The choice of thermography procedure also depends on the possible procedure we could implement. The simulation results here were verified by measuring the test specimens and thermography sequences, image processing by MATLAB Fourier transformation. The conclusion here, our measurement system, here you can see the real measurements. The conclusion is that the lock-in thermography can be used for detection with practical acceptable 10% accuracy of detecting defects in the Prepreg layer. Studies have been performed on up to 6-layer PCBs, which are the most commonly used. For each specific case, here we can see after Fourier transformation results, the place of the simulated, the measured defects in the samples. And for each specific case, however, it's the main conclusion. The parameters of the non-destructive flaw detection system must be previously selected, modeling and thermography simulation. Thank you. These are all my presentation.
Thank you, Doctor, for your presentation. I have a question. This thermography, if the material has a higher thermal conductivity or a lower or negligible thermal conductivity, how will this detection will work?
Sorry, how thermography work?
No, because if the material's thermal conductivity is a negligible or it's very minor thermal conductivity of the material.
Yes, by simulation, different defects in Prepreg material, I saw that this Prepreg is hidden under different conductive and isolated layers. This we modeling the defects, and
Your
after,
modeling, your modeling is modeling the material is the copper, right? You're working on the copper material.
yes, copper, also um, the whole structure of PCB, with
Because the, co- the, co-
defects
the, co- the copper has the higher thermal conductivity, and
yes,
my
yes, of
question
course.
is my question, if on the other side, if we have a lower thermal conductivity material, or the material has a negligible thermal conductivity, so how we can use the thermography to analyze the or to detect the fault or defects in the materials?
Yes, it's so
Could we do some things in the
yes, yes,
simulation?
yes. Yes, yes. After simulation, by using infrared thermography, we simulate by using pulse thermography, but using pulse thermography, the results is not well. We couldn't see defects in prepreg layer. But when we use optically locking thermography, we can see here. Here is the simulation results, and you can see in here copper layers. Here copper layers, and the defects in prepreg material. These in yellow are defects in prepreg,
The
and
yellow indicating the defects in the copper material. Am I correct?
no, yellow is defects in prepreg material. In
Okay.
red and in blue are copper layers.
All
Yes,
right.
black in black you can see uh, the prepreg material, and so this 2D 2D picture of the model. Yes, but here is the result after locking simulation of the structure, and we can show a shadow above the defect in prepreg material, but boundary can be seen. A good boundary we can see these defects here. Here, this one defect is situated only in prepreg, and there are not layers of copper layers above and under the prepreg material. But here, for here defects, we have 4 copy layers above and under prepreg materials, and also we can see after locking thermography simulation, the place of the defect in prepreg material.
Thank you very much, Doctor, for your very good presentation. It's a very interesting work. Thank you very much, Doc.
Thank you.
Thank you.